Okay. All right, so let's pick up where we left off. On Monday, we talked about computers, and we were mainly focusing on the hardware that's involved. Does anybody have any other questions now having been able to think about that for a few days? Anything you want clarification on, or? Okay. So now let's go over to the other side of it, which is the software. So none of the computer hardware is really very useful without software. We actually had the hardware long before we had the software. It took us a while to figure out how to get the computers to actually do something useful. So software is, you can think of that as like the bridge that converts like your ideas and instructions, like the things that you want to do, into instructions that the computer machine understands. Because the computer, you know, now that you understand a little bit about how that computer works, you can understand why just talking to it isn't necessarily going to get you anywhere. Because ultimately, what is the language that it understands? Yeah, it just understands those transistors, you know, going between 0 and 1. That's the only thing it understands. And so you've got to, if you want to get it to do something for you, you have to figure out how to distill or translate or whatever the thing you want it to do down to that level, okay? And that's what software does. Software is what does that translation, okay? And generally speaking, and this is more or less what Ada Lovelace said that we talked about last time, was like the computer can do anything that you can teach it how to do. So the computer doesn't know how to do really anything all by itself, but it is really good at following instructions. And so if you can figure out how to teach it to do something, it will do it, and do it in a very predictable way, the same way every time. And depending on how good your software is, really fast too. It can do things really quickly. Some things. It's usually like the things that take us a long time to do are the things that the computers do really quickly, and vice versa. Things that we do really quickly take the computers a long time. What's that?
Like what?
Well, like, for example, exercising wisdom. We do that really quickly. You know, we draw upon our previous life experience and place it in the context of what's in front of us and make a judgment about that instantly, right? That's a really hard thing for a computer to do. Even the most sophisticated AI models of today like struggle with that. You know, that's a real, it's called reasoning, and reasoning is like really hard for computers to do. Yeah.
Couldn't be me.
Yeah.
I love reasoning.
But you know, you ask them to do a bunch of math for you, and they'll do that all day at blistering speeds, you know, compared to you. I mean, something that would take you an hour, and a math problem would take you an hour to figure out, the computer can do it faster than you can blink. But the computer doesn't do anything that we don't teach it to do. We as human beings, right? That's just how it works. They haven't gotten to the point yet where the computer inherently teaches itself a whole lot of things. There is things like machine learning and artificial intelligence and stuff now, but that began with us teaching the computer how to do that, right? So far, it's like it always starts with us, which is like really important to remember, because another way of thinking about this is that, well, just remember, like, the computer can do it, but it just follows instructions. So it's not doing what you want it to do. It's like you got to think about, well, how is what I'm asking it to do not, am I not asking it in the right way, or am I not giving it the right instructions? I mean, because it's usually you that's the problem, okay? So let me just like give you a really, really simple example. So cooking, something really easy for humans to do. Humans can follow a recipe, a simple recipe, and make food out of that. That's something most people could do. Really hard for a computer to do, actually. But here's an example of a recipe for French toast that you would probably see written on a little card in the kitchen in your grandmother's house or something, right? So it's 4 steps, very simple instructions here. Does everyone feel like they could follow?
Step by step.
Could you follow these instructions, and are you confident you would get French toast
Yeah.
by following these instructions? Anybody feel like this would not work for you?
I'm not good at cooking. But
I
like,
feel like this is pretty easy. I like this recipe, so that's why I took a picture.
Yeah.
Hashtag maybe later.
Yeah. Okay. Good recipe, simple.
have you made it before using this recipe?
Yeah. Yeah.
Is this your recipe?
No.
Did you look up
Whose
French
recipe?
toast? You gotta think of one.
He's not thinking how to make French
Hey,
toast.
Yeah, it's
So-
right there.
Okay. But we could do this, right?
Yes.
We could do this. No one's feeling baffled by this recipe. No one's like, I don't understand it.
Oh, that'd be perfect.
I'm a little nervous.
Okay. All right. So,
Give it the acceptable range.
well, let's imagine what the computer would do if it followed these instructions. If we gave these instructions to the computer. There are some problems with these instructions. For example, we did not specify that we should separate the shells from the stuff inside the eggs. So the computer would be perfectly within the realm of the instructions to just throw the eggs entirely in their shells and all and beat them together, right? We did not, we're not be super specific about what to do with the bread. So it says dip 6 slices of bread. It could just like take all 6 and throw them in there all at once, which isn't probably exactly what we want. We also didn't really specify that we should make sure that both sides of the bread are covered with the egg mixture, right? So it's like there's a lot of little problems here with that whole dipping the bread thing. Like the computer doesn't, it's probably going to do that wrong. Now, in step 3, we didn't really specify what we're frying in the butter. So, I mean, the computer could conclude that it's supposed to fry the mixture in the butter, the egg mixture. We didn't say the bread, right?
You also didn't mention a pan.
Yeah, we didn't say what to fry it in.
Also didn't mention a bowl, so the computer could just pour
Yeah,
ingredients on
yeah,
the table.
right?
Like golden brown is subjective, but that's honestly,
Yeah.
that's a recipe problem in general. Like,
You gotta give it a cue.
That's why you have to.
Yeah, does the computer know what golden brown means? You know?
golden brown is.
Um,
I don't judge you.
I hate that.
we didn't really specify that both sides of the bread should be fried to golden brown, so the computer might very well burn that French toast waiting for the top to turn golden brown, right? So there are a lot of problems with this recipe if we were going to give it to a computer. This is like nowhere near enough information because the computer can't reason like you all just did. When I gave you this recipe, you all looked at that and you inferred all of that missing information instantly. And we're like, oh, yeah, totally, I can make French toast out of that. Computer doesn't do that. It doesn't infer all the things that are missing. It doesn't reason its way through this and work out the stuff that's not there. It just follows instructions. This is a quote from the American Library Association in 1964 when the UNIVAC computer, which was a really early, by today's standards, very primitive computer that was shown at the World's Fair. They said the computer is only a fast idiot. It has no imagination. It cannot originate action. It is and will remain only a tool to man. This is not changed, actually. I mean, they were right then, and they're still right, actually. This is true. I mean, even all of the innovations that have happened since 1964 in computing have not changed this fundamental observation that they made, which was spot on. Like, yeah, it's a fast idiot. And you got to remember that. Like, when the computer is not doing what you want it to do, you got to remember it's just a fast idiot, right? It's a way faster idiot than you, but an idiot nonetheless, right? So let's take another crack at this French toast recipe and see if we can, get it into something that would be more easily understood by the computer. So here is this is my first pass at a French toast recipe that the computer could follow. Now, this is all assuming that we had some sort of output device that could be used to control the utensils, right? And we're assuming we have an input device that can sense color and that can see golden brown and all that kind of stuff, right? So we've got to sort out the input-output sensors and devices, but let's assume for now we've done all of that. And then we give it these instructions. This is way more information than we need to make French toast. Yeah, but this is still not enough for the computer, but we're getting there. We're getting there.
You have to specify the butter.
Probably.
Have to specify what crack and beat means.
Does it imply that the computer knows what any of this means? Like, does it know what an egg is? How do we know the computer knows what an egg is?
Right. Yeah.
Well, I'm like, it's a computer. It doesn't know, like, yeah.
These are good questions, right? So we would probably have to start this program before we get to any of these instructions just saying,
These are what these things
this is an egg. This is bread. This is bread. This is a pan. This is, butter. This is,
This is what this term means.
yeah. We have to, small amount of butter, like we got to get more specific than that. We have to, some objective measurement, like what is exactly how much butter do we need? We're getting there, but you're starting to see the order of operations, right? Like, look at step 3, how we've broken step 3 down. We're just saying, for each of 6 pieces of bread, do this. Dip the slice into the mixture.
Feels like coding.
Exactly.
It is exactly so.
This is coding, right? So this is how you write software. And then, okay, for each side of the bread, do this. Put it on the pan. Wait 1 minute. Look at the bottom. If it's golden brown, then great. If not, repeat this step. And this step is wait 1 minute and look at it. Wait 1 minute, look at it. So eventually it's going to look at it, see golden brown, and then it's going to remove it and do it the other side, right? Because it's supposed to do that for each side. So it will flip it over and do the other side now. Wait 1 minute, look, wait 1 minute, look until it's done. Then it will take it out and put it on the plate. And then it will do that again for each slice, right? So yes, this is not enough yet, but this is the way that we have to think about teaching the computer how to do things. We have to be really, really specific. We can't infer anything. We can't assume that the computer understands anything. And we have to be really explicit about every instruction. So if you're going to write software, your own software, and you guys will do that. There is coding involved in sound. It's usually, some of you might get into actual, really lower level coding, but most of you will probably deal with higher level stuff like scripting or simply just automation programming and stuff like that, where you're either manipulating a scripting language or you're just leveraging, automation systems that are built into software, and you have to be really specific. Like, think about if you've ever, think about like the mixing console project that you did in my class, that final project where you're tracking all those VCA changes. You had to get really specific about what exactly you wanted the computer to remember for that scene and what you didn't want it to remember. You couldn't just assume that it was going to remember the right things. And there were people that just had it remember everything for every cue, which, creates a bunch of problems, because then if you change it in one place, it doesn't change everywhere else, right? The computer was doing exactly what you told it to do, and what you were telling it to do was remember way more stuff than you needed it to remember. So even if, whether you ever write actual C++ coding or not, you still have to understand how to think like this a little bit, because you absolutely will be doing some kind of programming or instructions to a computer many times in your life, especially if you continue to work in sound. Okay? Okay, questions about this? All right, so let's talk about software a little bit more. This is, if you take nothing else out of this little talk today, I hope it's this. Computers do what you tell them to do, not what you want them to do. Right? That's it. That sums up this entire lecture in one sentence. They do what you tell them to do, not what you want them to do. The most common thing I hear people say, it's not doing what I want. It's like, that's not what it does. It has no interest in your wants or your goals or your desires. It has no agenda. It doesn't care about you. It doesn't not care about you either. It is ambivalent about you. It just wants to follow instructions. That's all it does. It just follows instructions. What's that?
Follow instructions. I said that's all I want to do.
Yeah. Follow instructions. That's it. It doesn't get happy, it doesn't get sad, there's no satisfaction in it, there's no revenge, it doesn't get angry, and yeah. It doesn't get mad at you, it just follows instructions. You're the one who's getting mad because it's not working, and it's like, what? I did exactly what you told me to do. Why are you mad? Okay. You didn't say you wanted that.
You should have stated that.
Yes. So, all right, so let's talk about different kinds of software. Understanding how these different kinds of software stack on top of each other is really important, because when you're trying to understand, why is the computer not doing what I want it to do, of course, it's because you haven't explained yourself correctly, but it might be that you haven't really explained yourself correctly to the right part of the instructions. You might not have put your instructions in the right place. Okay? So there are 3 levels of software that we're going to talk about: application software, system software, and firmware. Okay? We're going to start with firmware. So firmware is the low-level software. And when I talk about levels, I'm talking about levels of abstraction. And these are abstract relative to the computer's native language, right? So really low level would be the language of the computer. High level would be meaning we have abstracted that language high enough to where we can understand it. Okay, so the lowest level that we're going to talk about today is firmware. And this is usually software that's embedded in the hardware somehow, like on those ROM or those EPROM chips or something like that. And it generally, what firmware does is it's really just about getting all the hardware to communicate with each other. So it just tells all the parts of the computer how to talk to each other. Tells the CPU how to talk to the input devices and output devices. Tells it where the storage devices are, and explains, how to access those. Okay, that's the firmware. And it's not always called firmware. It could be called something like BIOS or EFI. There's other things too, but it's usually that really low level, just hardware level code that just tells all of the hardware how to talk to each other. Okay. All right. The next one is system software. And this is sometimes also usually called the operating system. And what this does is it provides some sort of user interface to you, some sort of access to you to the hardware. So the system software is what allows you to communicate with the hardware. And it also has the ability to launch other programs, other software. And part of the operating system also includes a thing called device drivers. And what a device driver does is it's a little piece of software that tells the operating system and the firmware how to interface with some new piece of hardware. So if you introduce some new piece of hardware to the computer by like plugging something in, some new thing it's never seen before, it needs what's called a device driver software so to know how to do that. And the device driver software translates the operating system code into something that the firmware understands so that the system can use that piece of hardware. Now, a long time ago, you used to have to pay a lot more attention to device drivers than you do now. Thankfully, we've gotten a lot better at kind of creating device drivers that work with lots of hardware, and manufacturers are getting those device drivers built in as part of the operating system base code. But you still run into it every once in a while, where you have to install some sort of device driver to get it to talk to the thing. Okay, but that is a feature of the operating system is the ability to load in device drivers, which allows it to understand how to communicate with new hardware that isn't already accounted for by the system firmware. So examples of operating systems are like Windows, Mac OS is an operating system, Linux is an operating system, and within Linux you've got the different types of Linux. You've got Ubuntu and Fedora and those kind of things. And there's others too, like iOS, Android. Those are all operating systems. Okay. Now you got application software. So application software is otherwise known as apps. See where that comes from? Application software. That's what apps is short for. This is software that is a set of instructions that uses the capabilities of the computer to do something that you want to have done. So, for example, you want to type some written language. You want to write a paper. And like put the words, organize the letters and words onto something that looks like a page, right? And then check it for spelling and punctuation and all that kind of stuff. And like Microsoft Word. Back in the day, it was Word Perfect when I was a kid. And it came in a big box of floppy disks because it was such a huge app, and you had to it was like 30 floppy disks, like one at a time. You're like putting it in to get this whole thing going. Because you couldn't download it because the internet didn't exist. I know, that's just like blows your mind, but it really didn't. It really.
Did it take you to do that?
Oh, a long time. It was very exciting because you get this big, huge box full of disks. And you sit there all afternoon, like feeding them in one at a time, because it's like 1.4 megabytes each disk, and so you're like.
So, is this like all day tasks?
Oh yeah.
Like multiple days?
Yeah. No, I mean in an afternoon.
You
You know.
just turn it on and then go to bed and wake up and have
No, because it would have to ask you for the next disk. It's like asking you every 10 minutes for the next disk, and then it's like, okay, here's the next one, here's the next one, here's the next one.
That's crazy.
Can you still do that? Like, if I wanted to buy a copy of Windows on floppy disks or CDs or...
Cal tried to do this last year because he asked the same question, and he managed to like find some sort of emulator for an old DOS system, and then like actual like disk image files for the old floppies and stuff, and tried to install like AutoCAD version 1 into this version. I think he got it working. It took him a while, but
And then what? He just had it on his computer. Then?
I guess.
Like,
Yeah.
He only uses command line now.
Yeah.
And then in one click, it's gone.
Yeah.
That's funny.
So, so yeah, now thankfully getting this application software is a lot easier. When like I said, when I was a kid, like you had to go to the store and buy the software in a box and take it.
They still sell softwares at like the big boxes at Best Buy. Every time I walk past them, I'm like, wow, a relic.
Get him on Explorer has it too.
Yeah, not much, but
They've got like Photoshop and like Adobe products.
yeah, but like these days, it's not all that's in there is
Like a flash drive.
there's not even that in there. Like, yeah, it's just like a little card with a code on it, and you download it.
Buy sell it?
Yeah. So yeah, you had to go to the store and buy it, and it would be physical discs. And then once, like after the floppies, then it was like CDs, because that had a lot more capacity. You know, a CD could hold what, like 700 and something megabytes, which was, you know, a lot of floppy disks. It was like 500 floppy disks, which was like crazy.
I think we should measure everything on this.
There's a picture out there somewhere of like Bill Gates like sitting on a pile of paper that represented like how many documents could be stored on a single CD-ROM or something like that. Used to blow our minds. So, and then after that, it was like DVD-ROM discs. And then now you just download all these things from the internet.
Yeah, it's a cool picture.
Yeah, that's it.
That's a fire, actually.
So getting this software used to be really hard. You either had to make it yourself, or you had to go to the store and buy it, or you could get it from somebody else that had it. And we talked a little bit about shareware the other day, where that was kind of a big deal for a little while. Of just like, oh, I've got a little piece of software here. Let me make a copy of it on a disk, and you can have it, and then mail whoever made it $10. Like that was totally normal for a really long time. So now it's pretty easy. I mean, I learned to code in BASIC when I was a kid in school, because like sometimes that was the only way to get the computer to do stuff. And now you don't have to. Like, we've gotten good enough at this that you probably vast majority of people never have to understand at all where software comes from or how it's made or whatever. They just use it. But you do need a piece of application software for every specific task you want to perform. So you want to write a paper, you need an app for that. You want to edit audio, you need an app for that. You want to draw a picture, you need an app for that. Those apps are just a set of software code instructions. And that's kind of the really cool thing about computers, is once you've sorted out that firmware and that operating system part, which is the really, really hard part, then you have to just figure out a way to write instructions in plain English that a human could type, that then can translate those into the sort of machine code. It's called a compiler, that compiles those instructions into the format that the operating system can use to perform that task. And writing a compiler is a really hard thing to do. But there are people who figured it out. And so, it's pretty straightforward now. But the application software gets written specifically for certain operating systems. Okay, those compilers work for certain systems. And so, an application that was compiled for Windows, for example, doesn't necessarily run on the Mac OS. It doesn't necessarily run on Linux. It doesn't, So that's something you got to make sure of. Like, is the app that you want to use compatible with the system that you have? And that's not necessarily about the hardware. For example, QLab is compiled for the Mac operating system. And that is not a hardware problem. So it won't run on Windows. And that's not a hardware problem. Like, the hardware is not dramatically different between, at least it was honestly identical for a while there when Apple was using Intel processors in their computers. There was really not a significant difference at all between the hardware that was running Mac OS and the hardware that was running Windows. So the hardware was identical, but QLab still couldn't run on it because it sits on top of that operating system software. All right? So the app you want has to be compatible with the operating system software you're running in order for you to be able to use it on your system. And thankfully, the chips have gotten fast enough now that we can now kind of virtualize operating systems, which is crazy to me. So you can actually have a virtual computer. That's what Parallels and VMware does, is it creates a little piece of software that pretends to be computer hardware that you can then install a different operating system onto this pretend hardware, and then you can run an app on this operating system that is utilizing this pretend hardware. And that pretend hardware is ultimately utilizing your real hardware, but it's crazy. There's a website now that runs Mac OS 9.
Is that not like a copyright issue?
I mean, probably, but that's not the crazy thing about that. But the crazy thing is, like, Mac OS 9 used to require a computer that was as big as the one I had on this table to run. And now it's running on a web page. That's how far we've come.
I'm just surprised Apple has let that happen, you know?
I don't know that they care a whole lot anymore about Mac OS 9.
Like 16.
So anyway, there you go. All right, that's the end of this thing. Any questions about that? Okay, so now what I want to do is I want to go back to this, and you all saw this in December, but I want to look at this a little more detail, because now what I want to do is say, okay, so we understand what the computer hardware does. We understand now what the software does. Now, let's take a look at how you would utilize that hardware to do something like digital audio. Okay? So you have, this is an example of what's called a digital audio workstation. So most people, when they some people use the term DAW which drives me nuts, actually, because it's an acronym. And it actually doesn't mean what a lot of people think it means. A lot of people say, what DAW do you use? And it's like, well, I'll use Logic. Well, no, like, the digital audio workstation is not the software. It's the whole thing. It's the software and the computer that runs it and the interface and that whole thing. Like, that's the workstation. The software in and of itself is not a workstation. It's just an app. Now, Pro Tools is a digital audio workstation app, but it is not in and of itself a digital audio workstation. A digital audio workstation is all of this. So let's assume that we're recording and then playing back. So we'll start with the microphone. So that's our input device. Remember input devices from last time. So our input device is a microphone in this case, and microphones just take that sound wave and convert it into an electrical signal. It's called a transducer. And usually the computers, I mean, historically anyway, still today, the computers don't necessarily have built-in audio inputs and outputs. A lot of computers now will have built-in audio outputs. They may or may not have an audio input. They might have a built-in microphone now, but that microphone may not be really suitable for recording what you want to record. And the computer may not really have a hardwired microphone input as part of its base hardware. And if it does, it's not a very good one. And so you usually have to expand that using some sort of audio interface. And that's like what this Focusrite thing is that I'm using right now. That's another little computer that you can connect to your computer using some sort of data cable. These days, it's probably like USB-C, or it could be USB 2 or 3, or Thunderbolt or something like that. But it will have, the kinds of audio inputs and output connections that you need that are good quality, that low noise, balanced inputs, outputs, gives you good preamplifiers on them and everything. And then there will be some kind of device driver that lets it talk to each other. So that's what we're doing, is we're going to use one of those. So we plug that microphone into our audio interface, and the first thing it encounters is the preamplifier, which is no different really from the preamplifier on a mixing console. It's just a low noise amplifier that amplifies that low voltage signal to a higher voltage signal, but still pretty low voltage. I mean, it's only taking it up to 1.5 volts or so. And usually you're going to have some kind of knob to control that preamp, just like you would have on a mixer, and that'll be on that interface. Okay. Now from there, it's still analog audio, signified by this red wave. And then it hits this thing called the ADC, the analog to digital converter. What that does is it takes that analog wave and it converts it into binary numbers. And the pattern of binary numbers can be used to represent that analog electrical wave. We'll talk about how that conversion works in another class. So we'll spend a whole class talking about that ADC and what it actually does and how it does it. Okay? But for today, all you need to know is what it does, which is converts that analog audio signal into digital data that represents that analog signal. Okay? And then it runs through this thing called the controller. And this is like a little chip that is on that audio interface that kind of routes these signals around, does a little math on them, maybe some processing. It can do a little bit of work on this digital data that you've now created. And the controller will also facilitate communication between itself and the computer. Okay? So there will be a few different paths of communication here. So there's one that just like relays that audio data into the computer. Like that's one path. That's just the audio data. But then there's this other one that is like using this thing called the device driver, which I'll get to in a second. But that's like all of the control information. That's all the instruction set. So the controller is telling the computer what it's doing all the time. It's like, hey, I'm sending you something now. This thing that's coming in over here, that's input 1. Call that input 1. Right? And this thing that I'm sending in over here, call that input 2. And here's the information you need to know to understand that data. It's using this sampling rate. It's using this bit depth. It's in this format. So here's how you decode it. Like that's all happening here between the controller and the device driver. And what the device driver is doing is this is really that little piece of software that helps the operating system communicate with that extra piece of hardware that you've now added, that audio interface. So that's what that's doing. The actual audio data is going directly into RAM. This is really important to know. Super important. The audio, when you're recording, the audio data is streaming directly to RAM from the audio interface. It's not going to the hard drive. Not at first, anyway. The first place it goes is the RAM. And why is that important to know? Based on what we learned about RAM. Yes, Ace.
Important to have enough so that it goes fast, basically.
Well, RAM is pretty fast. But, you know, the do I have enough RAM? Yes, right? Because you know you have limited amount of RAM, so you want to have enough to collect that information. There's an even more important reason why it matters that it's going into RAM. Yes, Sam?
Because if you unplug the computer, the RAM just disappears.
Yeah,
forever.
right? So if you lose track of this somehow, it's gone, right? If that stream of data that represents your audio gets interrupted for any reason, it's gone because it's just sitting in RAM at first. And so you want to really make sure that, because sound is going to be this continuous stream of data, like it's never going to stop, and you can't lose any of it, and be able to reconstruct that audio back again on the other end. Like if you lose any of it, the rest of it that you've got is not super useful anymore. So you really want to make sure you don't lose any of it. And there are a lot of problems with, or potential ways you could lose it, because you're putting it into RAM, which is the most volatile part of the computer. It's the part of the computer that is most likely to screw it up. But it needs to go there because it's the fastest place to capture it. And so the way that we help make sure that we don't lose any of it, let's talk about what are the ways that it could get lost. After it goes through the RAM, it goes to the CPU. So the CPU can do whatever processing it needs to do on it and sends it to hopefully a storage device where it keeps track of it. But we know that the CPU has limits in terms of how much math it can do at any given time, right? We know it can only do one thing at a time per processor. Now, these days computers have multiple processors in the CPU, so it can do several things at a time, but it's still it's a limited amount of things the computer can do at one time. It's not infinite. So what if your audio data is coming in faster than the computer can process it, than the CPU can process it? What would happen? Yeah, it's just like it can only pay attention. Think about when you get like overloaded, right? Like you've been fed too much information and you're trying to keep track of too many things at one time. People start throwing new things at you. What happens? You freeze, right? Like, or you just don't even hear that information. You drop it. Like, it doesn't get collected. Same thing happens to the computer. Like, if the computer's busy, it doesn't have any ability to collect anything new. But audio never stops. And so you're just still sending it in. And if it has no ability to catch that ball because it's got balls in all of its hands already, it's just going to drop that data. And you don't get it. That handoff between RAM and the CPU just like doesn't happen. And the RAM just keeps dumping it, dumping it off to the CPU, and the CPU can't take it. So it just gets dropped. Or the RAM fills up, waiting for the CPU to take it, and then when the RAM fills up, there's nowhere else for the new stuff coming in to go, and so it just doesn't go anywhere. This is how you would lose it. And so you have to think of a way to like make sure that doesn't happen. So the way that we handle that is using this thing called an input buffer. So the input buffer is for every stream of audio data that you're collecting, you create an input buffer. An input buffer is a chunk of your RAM storage. So it's a little bit of your RAM, and you decide how much. Could be enough RAM to store. I mean, generally the biggest buffers you're going to see is like 2,048 samples. That's the biggest RAM buffer that I think, and that's huge. I mean, most people don't.
You said
2,048 samples. That would be an example of a really big RAM buffer. These days, the computers have gotten fast enough that you can get away with like 64 to 32 samples in a RAM buffer, and you're okay. But when I started out, you were doing 1,024 to 2,048 samples in your RAM buffer. In other words, you're allocating a certain amount of that limited RAM, right? It's a finite amount of storage you have there. You're going to assign a chunk of it to a single audio signal. And what that is it's just kind of like it's a waiting room for that endless audio data to like collect while it's waiting for the CPU to process it. And this way, because the CPU is doing a lot of other things besides processing your sound, right? It's giving you the notification that someone liked your Instagram post, and it's checking to see what time it is, and it's checking to see if there's a software update available, and it's refreshing that web page that you have running in the background. It's playing that episode of The Office that you're running. It's doing all of those things all at the same time, usually, as I see what you guys do on your computers. You've got like 20 things going all at one time. And so the computer's busy. It's like doing a lot of other things that have nothing to do with processing all this audio you're streaming in or streaming out, because the output part works the same way, just backwards. And so it's not going to process that audio at a consistent rate. Right? Just depends on how many other things you're giving it to do. So how many balls is it juggling? Sometimes it'll like do a bunch really fast, and then it'll like hang on a minute and pay attention to delivering you that next 30 seconds of The Office, and then it'll go back to like working on the next part of your audio, and then it'll go check what time it is, and then it'll come back to your audio, right? So it's going to do it in fits and spurts. And so the RAM buffer is like when the CPU says, hang on a second, I got to do something else, the audio has a place to kind of like fill up while it's waiting. And then when the CPU says, okay, I'm ready now, it'll take whatever's waiting and do that. And what you're trying to do is build a large enough buffer that the RAM will remember what's coming in and feed it to the CPU when it asks for it. And the CPU has to be able to pull it out of that RAM buffer faster than that RAM buffer fills up. Okay, so that's why you kind of have to manipulate the size of that RAM buffer a little bit sometimes. Is if the computer's acting really slow, if it's doing a lot of work, you may need a bigger buffer in order to not lose data. Okay? The problem is, the bigger the buffer, the longer your latency is. Because, the bigger that buffer is, that just means that that's an amount of time you have to wait before you get to hear the result of what you're doing. So there's a balance there you're trying to strike. Because if the audio is waiting to be processed inside that RAM buffer, that means you don't get to listen to it while it's waiting. Okay? So sometimes if you find that either when you are recording or playing sound back, if you hear the audio is kind of dropping out, or you're getting like playback errors or something, like it's just like stop. Sometimes Logic will do that. It'll just be like, I couldn't keep up. Or QLab will like just start dropping things. Like what's happening is that, like you've given the CPU too much to do. It can't process all of that fast and do everything else you're asking it to do. Like it tried to update your Instagram notifications, and that was like too much. It couldn't do that and deliver all this audio at the same time, and so it just drops it. And when you find that that's happening, that's a sign that you need to increase your buffer size, your input or your output buffer size. If you find that there's too much latency, for example, when you're recording, and let's say you're recording somebody talking, and they're talking into the mic, and they're listening back through the computer what they're saying, if there's a noticeable delay, if like they talk and then 100 milliseconds later they actually hear their voice back, that can be really hard to perform when that's going on. That's a sign that your input buffer is too large, and you got to figure out how to shorten that so you can get that round trip shorter. And you can do that. You can make that buffer smaller, but you have to make sure that you can make that buffer smaller and still be able to deliver all the audio and not drop anything. And the best way to do that is to close all those other apps and give the computer the ability to assign every resource it has available to keeping up with that audio. You have a question?
Yeah. If you were in that situation, is the the latency from the input buffer enough and noticeable enough that that's legit what you would be like, this latency is probably from that?
Yeah.
Okay, so that's like your first thought if you're dealing with.
For me, yeah.
Okay.
Yeah. So same thing happens on the output side. So you're playing audio and the CPU is like processing it, sending it out. Well, same thing, it maybe can't send it out continuously. It has to check on other things here and there. So you want to have an output buffer in your RAM to just sort of like buffer all of that so that what's coming out of the computer is a steady stream and never gets interrupted. And it has all the same issues as an input buffer, but that goes back out to your interface through what's called a digital to analog converter chip, which does the backwards thing where it takes that digital data, converts it back to an analog wave, out a physical output, which would go to your headphones or your speaker or whatever, right? Now, what's happening inside the computer? So it goes into the CPU. The CPU is doing whatever you've asked it to do. It's running the operating system, and on top of the operating system is sitting a program like Logic or something, and it's doing all of that math and processing and EQing and mixing, and which is ultimately just math that it's doing on all that data. And then it's got to put it somewhere. Like, let's say you're recording, right? And you've got this audio coming in. It goes in through the buffer. It goes to the CPU. And Logic is doing whatever it needs to do. Well, you want to remember this, right? This recording. You don't want to have to do it again. I've had some experiences where we didn't quite catch it, and we've had to do the recording again, and that's really frustrating. So you want to put that somewhere. Well, what are your options? Well, you can use the internal drive of the computer, which is this. But that drive's probably already pretty busy because it's running the application software, it's running the operating system, it's running all the software for the device drivers. It's doing a lot of stuff. The drives have gotten a lot faster now, for sure. They've got a lot more bandwidth than they used to. But it's a good idea, especially in audio, to do a dedicated hard drive, that the only thing that drive has to do is audio. It's not running anything else. And in fact, there are some audio software apps like Pro Tools that say, we will only certify the performance of our software if you are using a dedicated audio hard drive. Like when Pro Tools says, this is how many channels you should be able to record and play back on with this many plugins or whatever, like that is only true if you are using a dedicated drive for audio. And if you're not getting that performance and you reach out to the tech support for them, one of the things they'll ask you is like, well, where are you running your files from? Like, what's your recording drive? And if you say it's the internal drive, they're going to say, well, you can't do it that way. We make no guarantees that you'll get the kind of performance we've promised when you're running on the internal drive. So you've got to have an external drive that's doing that audio as a dedicated drive. And that'll help. That'll help a lot. And then, of course, the software is going back and forth. You've got the monitor that shows you things. The CPU is delivering that information. And in fact, sometimes, back when the computers were a lot slower and we had to pay a lot more attention to exactly how we were utilizing all these CPU cycles, a lot of the audio software had the ability to control the graphics refresh rate. Meaning, like, how often do we really want the picture to change? Because the faster we want the picture to change, that means the CPU has to spend more time and effort updating the picture, which could mean it doesn't have enough bandwidth available to keep the audio going. And so sometimes what we would do is we would say, yeah, dial back the refresh rate on the screen or something. I don't need to see that meter refresh quite so fast if that'll free up some resources to make sure we never drop any samples on the audio. Thankfully, again, we don't have to do that a whole lot anymore. But if you notice, if you ever look at the technical specifications for your computer, it'll usually tell you how many monitors you can have at one time on that computer. I mean, that's because they've done the math. They're like, yeah, here's that amount of work that you put on that CPU. It could reasonably do the amount of work it would take to drive 2 monitors and still have enough left to run all the different apps that we could imagine would be running. And that's what that's about. Like, they've only allocated a certain number of resources for that because it's shared. Okay, questions? So let me show you then some examples of this. Like, let me just pull up Logic here. And I'll do this. Okay. So here it is, and I'm just saying, hey, let's go ahead and record input 1. So it's doing it right now. But if you go in here to the settings and to the audio settings, here's I/O buffer size. Here's where you control that RAM buffer. And the options it gives you are 32 samples to 1,024. It doesn't even give you the 2048 anymore. But what's interesting is, so it's defaulting to 512. And what it's telling you is, based on the sampling rate you're running, it's done the math, and it is a 27.6 millisecond round trip to go through an input and output buffer of 512 samples. Meaning, if I try to listen back to this microphone on my headphones, I will hear my voice 27.6 milliseconds after I start speaking. Like, that's the amount of delay. If you're just playing back, like you're not recording, you're just like, you've already got audio in there, you're just going to hit play and play it, there's a 13.7 millisecond gap between when you hit play and when that sound comes out. All right? And that's just based on your buffer. Well, what happens if I increase it? I take it to 1,024. Okay, well, now it's almost 50 milliseconds round trip. That's definitely enough for even an untrained person to hear that difference, right? If you were going to bring an actor in or record them, for example. Whereas if you take it all the way down to, let's say, 32 samples, well, that's only 7.6 milliseconds round trip. No one's going to really notice that. Not in any way that's going to matter a whole lot. Okay? So this is where you manipulate that. There's some other stuff you can do here where you can kind of give it some instructions about how to utilize the resources of the CPU. So, like, how processing threads are like, the CPU a thread is like a stream of data that the CPU is working with, and it can have only so many threads at one time. So that's a thread. You can think of a thread like, it's a bit of work that's being done. And if you just do automatic, a logic is going to try to allocate the work you're asking it to do across whatever number of threads it thinks it can give the CPU that are available. So the CPUs may be busy doing other things. It's using some of the threads for other things, but if it thinks it's got a certain amount available, basically logic will try to figure it out. But if you have other things going on, and you need to make sure that logic has a very specific number of threads going, and that's never going to change, then you can specify that here. You can say, hey, I want you to reserve 10 threads for this. And that they're saying that is going to lock out 4 of your high performance cores. And what that means is this particular computer, the CPU on this computer, let's see if I can show it to you. So the CPU on this computer has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 processing cores in it. Now, generally speaking, I think it looks like, yeah, so 6 of those are efficiency cores. So these are processing cores that are really, really energy efficient. And it has 4 performance cores that are like, yeah, we're going to work, this core is tuned to work really fast, and I don't care how much electricity it uses or how much battery life it uses. Right? So one of the ways that it manages your battery life, makes your battery not die, is it tries to redirect as much towards the efficiency cores as it can, because they don't drain your battery as fast. But they're a little slower. But so what logic's telling you is, like, if you want to reserve 10 processing threads for logic, it's going to do that by locking out all 4 of those performance cores. So those performance cores are going to be dedicated to logic, and nothing else is going to get to use them. And maybe that's what you want. But like, if you're wanting to have something else running that also is going to need to use those performance cores, they're not going to get access to them. Okay? So you have the ability to tune some of this. We used to have to do this a lot more than we do now. We used to have to pay a lot of attention to how we were utilizing all of this. Now, most of you have probably never had to worry about it. How many of you have ever manipulated input buffers and processing threading settings? Ace has, maybe a little bit. Okay, so a little bit, but it's not a common thing anymore. But I wanted to show you what these concepts look like and how they appear. You can, in terms of multi-threading, this is like the extent to which logic is going to try to distribute the processing load across multiple threads. You can say, how do you want it to do that? It defaults to playback and live, meaning it's going to multi-thread both the recording tracks and the playback tracks. But you can say, just multi-thread the playback tracks and don't thread the live stuff. Just keep that dedicated to a single processor. Generally speaking, like, I would say multi-thread as much stuff as you can. You'll get better performance that way. The only reason maybe you wouldn't want to do that is, again, if you're going to really try to get your computer to do a lot of things at one time. If you're going to run several apps at a time on your computer, you might want to think about something like multi-threading, because multi-threading means that logic is going to use more of those cores, which makes it harder for other apps to use them. Okay. Okay, so let's look at something like QLab. So if you go over here to the QLab preferences and to this hardware tab, here's where you set your buffers. And it has a separate buffer for every audio interface on your computer, because QLab can talk to multiple audio interfaces all at one time. That's what it does. And so you've got, again, it ranges from 16 to 1024. But QLab also handles live input, so this would be a round trip. If you set it to 1024, that means each way. 1024 in, 1024 out. So that's the 2048 round trip. That's a pretty long buffer, right? So this is where you set that. And there's been time. There will be times when you're working with QLab and you're getting audio dropouts, and it's because you're filling up your buffers too fast. And you can increase these playback buffers, take them up to 1024, Now, the danger, the bigger you make that buffer, the longer it takes to hear the sound after you press go. Yeah?
Can you change like the buffers while you're working, like the set size not to change them back and forth, and like leave it at one number after you've moved it up, or can you move it back down?
Yeah, I mean that's probably not something you want to be like messing with while you're playing stuff. But you're really just kind of like you're looking for what's the sweet spot, right? What's the buffer that is big enough to handle what I'm trying to do, but not so big that I have latency that I don't. So you're looking for that sweet spot, and it just depends. It depends on what you're doing. So if you have a problem, then change the buffer size and then work for a little while and see if the problem happens again. But the reason why you wouldn't just like go to the biggest buffer possible is that then you have latency. 1024 sample buffer is time between when you hit go and when you hear the sound. So just want to be aware of that. But so that's where you manipulate that. Okay. And every audio program that is what I would call professional quality is going to have some ability to manipulate stuff like this. You're going to be able to see what the buffer sizes look like. You're going to be able to decide what you want to do. You might even have a control over how the processing is handled, how you're utilizing the resources of the CPU. You're also going to be able to talk about how it handles the data. So audio recording path. This is in Logic. This is where you're saying like, hey, when the audio is coming into RAM, it goes to the CPU, and then it has to go to a drive somewhere to be remembered. What drive is it going to by default? Like if I don't specify, where is it going? Is it going to use the internal drive, or is it going to use an external drive? What's it going to use? You can set that. Now it defaults to the project, which means right now the project is just an untitled one that it just created, and that usually is it creates that on your startup drive. So if you haven't hit save yet and saved this project to an external drive, and you just start recording, it's going to use the startup drive as your recording path because that's where it creates the new untitled files. Is it just puts them on the startup drive. But you can specify. You can go in and say, like here's where it goes. It goes to your home folder, the music folder, Logic. That's the default drive. But you can say, hey, take it to my external. Meaning when I'm recording, no matter what, even if I haven't like saved yet the project yet, always dump that audio straight to the external drive in real time. That'd be a really good idea, actually, because then you're not chewing up resources of your startup drive to do that when it needs to be paying attention to things like running the operating system, which is super important. Okay. And if you can default it back to project. What I usually will do is I don't usually manipulate this in Logic. What I will do is I will just, when I open a new file like this, I will immediately do a save as and just save it. If I save it to the external drive, then that's now where the project is, and therefore that's now the recording path. So new audio gets recorded to the drive where the project file is sitting. That's Logic's default. Okay. But I've seen it happen before where folks will do a recording and they'll just launch an empty thing like this, they'll start recording, and then they'll get 10, 15 minutes into their recording and suddenly Logic crashes and says, yeah, I'm out of space. And it's because you've got your startup drive is filled to the brim with episodes of The Office that you've downloaded. And you're streaming directly to that startup drive, and it's full. And it does not have a lot of room for a whole bunch of tracks of audio streaming in real time. And I've seen that happen many, many times. So another reason to use the external drive. Okay. How are we doing? You guys had a lot more questions last week. Yes, Monday. Thank you.
The last week I was.
Take us back a little bit, but I think I'm confused about threading.
Threading?
Yeah, like what it actually is doing.
Yeah. So threading is very similar to that concept that we were talking about the RAID drives. So you've got your set of instructions, right? It's like, here is the job I need to get done. And that job is process these 10 channels of audio, mix them together, add these plugins to them, and then send them out to the drive. That would be the job to get done. And that job is going to require a certain amount of processing power to do. Now, the software could take that whole job and just give it to a single processing core and say, all right, that's your job. You accomplished this job as fast as you can do it. And it will do it as fast as it can do it. The question is that as fast as you want it to do it? Like, let's say the job is bounce this project. Right? You're going to bounce this huge logic project to a bounce down, mix down file. Great. That's a big job. If it just gives that to one processing core, that one processing core is going to do that math as fast as it possibly can to write that file. But it can only do so much, right? So fast. If you want it, and so you might be sitting there waiting for a while for it to finish doing all of that if it was going to one core. But if you're willing to let it use multiple cores, then what it'll do is it'll take that job and it'll say, all right, here's the whole job. And it'll take 4 separate processing cores. And it'll say, all right, core 1, you take this part of it. Core 2, you take this part of it. Core 3, you take this part. And core 4, you take this part. You handle the plugins. You handle, the mixing. You handle the sample rate conversion. And, you handle the mastering, plugin right at the end. And that's called threading. Okay, so it's going to take that job and split it up into multiple threads, and the net result for you is you will be waiting less time for that project to get done, for that bounce to get done. It'll give you the file sooner. That's threading.
Can you go back to the settings real quick?
Yeah. Processing threads.
Okay, that's deciding how many cores you're going to use, and then the other one's deciding what you want it to do. Multi-threading was playback or
Yeah, so
playback and
here
load?
you're just saying, like, do you want to exercise some control about, how many processing threads are available to logic, right? My mic just fell off. Sorry about that. We just heard some. Yeah, there you go. All right, so if you want to decide like how many threads are available to logic to distribute this work, you can do that. It defaults to just automatic, which honestly is probably the way to go because Apple makes logic, and Apple understands how the operating system works, and it also understands how the hardware works. Like, it's made the hardware, the operating system, and it has made this application software. So it knows what kind of hardware it's running on, it knows the capabilities of the operating system, and it's going to find the optimal way of getting that done, probably. But if you find that it's prioritizing things differently than you want, again, because you have 20 things running on your computer at one time, then this is where you can get a bit more specific. And then the multi-threading here is just saying, like, which things will be threaded. So this is how many threads are available. This is what things are going to be threaded. Playback or playback and live. Because those are the two main things logic does. is it records live tracks and it plays back recorded tracks. Now, as the bouncing part, I'm not sure what that's accounted for. If that probably counts as playback, is my guess, but I'm not positive on that. But generally, in most cases, you're probably not going to need to worry about the threading. But I just wanted you to see the concept in practice, right? That these days, it's like, I think it's so great that you guys don't have to care about this. I used to have to care about this a lot. And you don't have to. Like, the computers have gotten fast enough now, and the software's running really well and everything, that you may never have to worry about the threading settings in your workstation software. But it is happening under the hood, and I want you to know that it's happening. There will be at least a time or two in your life where you will run into a buffer problem. If it hasn't happened already, it will. And it probably has happened to you before, and maybe you just didn't know that that's what was going on, and that's why you were having that problem. But it absolutely happens. And this is why it's a good idea to get as much RAM as you can on your computer. Because nowadays you can't change it. Used to be you could upgrade your RAM, you could add more RAM later. You can't really anymore, especially not on these laptops. So it's like a good idea to get as much of that. You can add more hard drives forever. You can daisy chain as many Thunderbolt drives as you have money, but like adding RAM is not really possible.
Why did they make it so you can't like add RAM on anymore? Is it because they want us to like buy the new thing that has more RAM? Or?
No, it's because they want to make the MacBook smaller.
That's annoying.
Yeah, they want to make it smaller and lighter.
Mine is still like
And to make the RAM upgradable, they have to have slots for the RAM, and the slots are big, so the laptop's thicker. So they can make it smaller and more efficient if they solder the RAM into the board. And if the RAM is soldered to the board, you're not going to upgrade it. So that being said, the new the Apple processors now, the M series processors, are super efficient in the way they utilize the RAM. Like, it's crazy, actually. The mileage they're getting out of their RAM is, I mean, it seems like it's like what 32 gigabytes of RAM used to feel like can now be accomplished with half that on these M series processors. They're getting so efficient with that, which is just really cool. So anyway. All right, that's it. We're done. So we don't have class on Monday, but we will be back on Thursday, and we will talk about binary, I believe, is what we're doing next. So now we're going to actually start to learn the language of the computer. Okay? There you go. We're done.